All right, let's talk about something we see every single second of every day, but maybe don't really think about. Motion. I mean, everything from a simple leaf falling to a car just zipping down the highway, our entire world is constantly on the move. So let's dive in, right? Let's figure out the surprisingly simple rules that make it all work.
And I'm not kidding when I say everything. You know, there's this great quote that puts it perfectly. Think about it. Even when you feel like you're sitting totally still, you're actually on a planet that's spinning, which is orbiting a sun, which is itself flying through our galaxy. It's just mind-blowing. Motion is happening on every possible scale you can imagine.
So that leads us to the big question, right? How in the world can we describe all this chaos, with just a simple set of rules? How do physicists take something so huge and, well, boil it down into a language that lets us actually predict what's going to happen next? Well, that's exactly what we're going to unpack today.
Okay, first things first. Before we can really get into the good stuff, we've got to make sure we're all on the same page. We need a common language. So let's start by defining some of the absolute basics.
And it really is this simple. Is something in a different place than it was a second ago? Yep, then it's in motion. Easy as that. Now, to keep things from getting too crazy, we're going to focus on the simplest type of motion, which is called rectilinear motion. Sounds complicated, I know, but it's really just a fancy term for moving in a perfectly straight line.
Okay, here's a little trick, a simplification that physicists use all the time to make life easier. Imagine a car driving 100 miles. Do we really care about the size of its tires or the shape of its hood to figure out how far it went? Nah. We can just treat the whole car as a single dot, a point object. This is so powerful because it lets us ignore all the complicated details and just focus on the movement itself. And suddenly, the same rules that work for a car also work for a tiny baseball or a massive planet.
All right, so we've got motion down. An object changes its position. But how do we talk about how it's moving? Like how fast? This brings us to our next big idea, velocity. And trust me, it's a little more interesting than just what you see on your car speedometer.
Let me ask you this. Think about the last time you were on a long drive. You might tell your friends, yeah, we averaged about 60 miles an hour. But at any one moment during that trip, what did your speedometer say? Maybe it was 70, maybe 45. Maybe you were stuck in traffic and it was 0. That difference right there is absolutely key.
And boom! That road trip example just gave us the two flavors of velocity. You've got your average velocity, that's the big picture, the summary of the whole trip. But then you have instantaneous velocity. Think of it like a photo, a snapshot in time. It's what's happening right now. And more often than not, that's the one physicists really want to know about.
So people use speed and velocity interchangeably all the time, but in physics, they're different. What's the secret ingredient? Direction. That's it. Velocity cares if you're going forward or backward, so you can have a positive velocity or a negative velocity. Speed just doesn't care. It's the number on the speedometer, pure and simple. 24 meters per second is 24 meters per second no matter which way you're headed.
You know, in the real world, we almost never move at a perfectly constant velocity. Life's just not that smooth. We're always speeding up, slowing down, changing things. And that change, that's what physics calls acceleration. The best way to picture it, just think about the pedals in your car.
Okay, let's look at the official definition here, because this is super important. It says it's the rate of change of velocity. See that? It doesn't say speed. And since we just learned that velocity includes direction, this is a game changer. It means acceleration isn't just flooring the gas pedal.
So when are you actually accelerating? Well, obviously when you speed up. And when you slow down, yep, hitting the brakes is a form of acceleration too. But here's the one that trips people up. You're also accelerating when you just change direction. Even if your speed stays exactly the same, if you're turning a corner, you are accelerating. Pretty cool, right? Any change to velocity counts.
Okay, deep breath. We've got our basic language down. Motion, velocity, acceleration. Now we get to the magic. This is where we get our physicist toolkit, the formulas that let us literally predict the future. Well, the future of a moving object anyway. Let's talk about the kinematic equations.
But before I show you the equations themselves, let's meet the main players, our cast of characters. There are 5 of them, and you'll see them over and over. First, there's x for displacement. That's just how far you've moved. T is for time, of course. V0, we often say V0, that's your starting velocity. Then V is your final velocity. And last but not least, A for acceleration. Got 'em? Good.
And here's our first equation. I love this one because it's just so simple and makes perfect sense. It says your final speed, v, is just whatever speed you started at, v naught, plus however much you sped up. And how much you sped up is just your acceleration, a, multiplied by how long you were accelerating, t. That's it. So simple, but so powerful.
All right, equation number 2. This one is all about figuring out how far something went, our displacement, x. It's kind of got 2 parts. The first part, v naught times t, tells you how far you would have gone if you just kept cruising at your starting speed. The second part, that 1/2 at squared, that's the extra distance you cover because you were accelerating. And that little squared on the t, that's super important. It tells us that your distance grows way, way faster when you're accelerating. And for our last trick, we have this beauty. What's its superpower? Look closely. There's no t. Time is completely missing from this one. This is your secret weapon for when you have no idea how long something took. If you know how far something went and how much it was accelerating, you can figure out its final velocity. No stopwatch needed. Okay, so we've got all this theory, all these letters and numbers. That's great, but what's the point? Let's put it to the test. We're going to use this stuff in a real-world situation where, honestly, understanding the physics can actually save your life. So I've got a question for you. A real gut check. Imagine you're driving and you have to slam on the brakes. Now, what if you were going twice as fast? Does it take twice the distance to stop? I mean, that kind of feels right, doesn't it? 2 times the speed, 2 times the distance. Let's see if the physics agrees.
And the clue is hiding in that last equation we looked at, the one without time. If you do a little bit of algebra, you set the final velocity v to 0 for a full stop, and solve for the distance x, you find something pretty shocking. The stopping distance isn't just proportional to your speed, it's proportional to the square of your speed. So what does that mean? It means it takes 4 times the distance to stop. No way! You double your speed and your stopping distance quadruples. Think about that. The difference between going 20 miles per hour and 40 miles per hour isn't just 20. It's the difference between a safe stop and a catastrophe. And that is exactly why the speed limit in a school zone is what it is.
So this is the real takeaway. You know, these formulas, they're not just homework problems. They describe how the world actually works, and they have very, very real consequences for our safety every single time we get in a car. Want to try some of this out for yourself? You totally can. Grab a friend and a ruler. Do this simple ruler drop test. You can actually measure the distance it falls before you catch it, plug that distance into one of our equations, and calculate your very own reaction time. It's a super fun way to see this physics working in real time.
So there you have it. We started with the basic idea of motion, built up to velocity and acceleration, and even got our hands on the tools that let us predict it all. So I'll leave you with this one final thought. The next time you're out in the world, what are you going to see differently? A ball flying through the air? A car coming to a stop? Will you ever look at simple movement the same way again? Thanks for joining me.